With the theoretical section now all done, we can begin with the experimental part. With this setup, we can measure the CHSH inequality as well as perform quantum state tomography.
This experimental setup is divided into two parts, the entangled photons generation and their measurement. First of all, we need a light source. In our case, we use a 405 nanometer wavelength blue laser that produces horizontally polarized light. In order to align the light beam in a precise manner, we use two mirrors and send it to the main part of the optical setup. Now, to produce the entangled photons, we need some kind of material that is able to produce them upon excitation. For this experiment, we use these two Barium Borate crystals that, through spontaneous parametric down conversion, are able to generate pairs of entangled photons. For those of you who don't know, spontaneous parametric down conversion is a nonlinear optical phenomenon that converts a photon into two photons with double the original wavelength. And in this case, this pair of photons become entangled when they are generated. This only happens when the polarization is in the same plane as the optical axis of the crystal and the propagation direction. Having said that, the first crystal can only be excited with the horizontally polarized incident photons and then generate a pair of vertically polarized ones. On the other hand, the second crystal does the same for incident photons with vertical polarization and produces horizontally polarized photons. One of these photons goes through the signal channel and the other through the idler. So, for our measurement, we require a superposition of horizontally and vertically polarized light, which is equivalent to diagonally polarized light. For this, we use a half-wave plate set at an angle of 22.5 degrees just after the laser. To further ensure the desired polarization, we also use a linear polarizer set to 45 degrees. The next optical element is another half-wave plate that introduces a relative phase shift between the horizontal and vertical components of the light, which will compensate the difference in the optical path introduced by these two BBO crystals. Let's move to the measurement part. To separate the photons in each channel, we use a polarizing beam splitter, these elements here, which reflect the vertically polarized photons and transmit the horizontal ones. Before the polarizing beam splitter, each generated photon goes through a quarter wave plate and a half wave plate to transform the photon polarization into a certain angle. As a result, the set made by these plates and the polarizing beam splitter can measure photons polarized in one direction and it's orthogonal. In other words, by varying this angle, we are changing the base in which we measure.
Now, once this is done, the photons are then collected by these lenses and sent over through the fibers to the single photon detector. This consists of 4 avalanche photodiodes which, when a single photon arrives, generate an electrical signal which can then be processed through additional electronics. In this particular case, we have a quad-channel real-time coincidence counting module designed in-house, which is responsible for detecting and computing the number of coincidences among the different channels in a given time. So, for example, let's say a photon comes into channel D and then a different photon comes into channel A at the same time or within a small time window. Then, this module will mark it as a coincidence and add 1 to the number of coincidences for the A and D pair. Now we do the same for all the other 5 possible combinations, and we've got a coincidence counting module. Bear in mind, it's very important that the device be fast, since it needs to be able to process signals which are just 10 nanoseconds long. It's also of high interest that the coincidence detection be made in hardware instead of software, so that the coincidences are computed in real time. With this in mind, I'll show you how it works with an example. Given the fact that this setup is designed for undergraduate level curriculum, the chosen interface must be familiar. So in this case, the data acquisition is made with a Python Jupyter script, in which the necessary steps are laid out in order. Now this setup is designed for 2 different experiments. You can either make 4 measurements and compute the S parameter for the CHSH inequality violation experiment, or make 9 measurements and compute the tomography for the entangled state. Today, we'll be doing the first one. After making sure the setup is correctly aligned and calibrated, we can start with the first measurement. Now, Laia, I would need you to please set for the signal lane the half-wave plate to 0 degrees and the quarter-wave plate to 0 degrees as well. Now, for the idle ring, the half-wave plate to 11.25 degrees and the quarter-wave plate to 22.5. Now, if you can please turn off the light, we can start the first measurement. Now, with the lights turned off, we can begin the experiment. Now, if we begin the measurement, we can very soon start to see how much larger the counts on HH and VV are opposed to those of HV and VH, which is to be expected given the basis in which we're measuring. Now, after 10 seconds, we'll have a complete measurement. This is the amount of counts for HH we have had in these 10 seconds. This is the one for VV, HV, and VH. And these four numbers are just the amount of individual counts for all the four detectors.
As explained in the theory video, the CHSH inequality stipulates the expected range of values of a statistical parameter, commonly referred to as the S parameter, which yields a value between -2 and 2 in the hidden variables theory, and in the quantum entanglement framework between -2 square root of 2 and 2 square root of 2. To calculate this parameter, we need to calculate the value of four correlation functions, one for each basis in which a state is measured. This can be expressed as the sum of these probabilities, which in this experiment depend on two parameters, the angle of the half-wave plate and the quarter-wave plate.
Having obtained the number of coincidences for each set of angles, disregarding the accidental counts, we can then compute the probabilities like so, in which NRC represents the number of real coincidences and N total is the sum of all the real coincidences for every measurement in the same basis. Note that in total we carry out 4 sets of measurements, each represented by a color in the table. Now, if we compute the values of E, we get the following table. And then we can compute S. And we find that the absolute value of S falls between 2 and 2 square root of 2, which is approximately 2.828, which effectively violates the CHSH inequality, disregarding the validity of the hidden variables theory and hence supporting the existence of quantum entanglement.
We did it!